My name is Ian Dennis Miller from the University of Toronto, and I will be presenting our work on how context variability promotes generalization in reading aloud. Let's start with an example of a reading aloud task. A regularity is when several words share similar pronunciations, like the int in hint or mint. If we were asked how to pronounce a new item, like F-I-N-T, we would probably extend this regularity to this pronunciation and pronounce it as fint. When a word like R-I-N-T is pronounced to rhyme with pint, instead of the more common pronunciations associated with hint and mint, this is an exception. Our knowledge of how to pronounce other words does not generalize very well to this exception. And somewhere in the middle are ambiguous pronunciations. A non-word, like B-I-V-E, could be pronounced like give, or it could be pronounced like dive. So it's ambiguous, biv or bive, and only some of our previous knowledge is going to generalize. But these classes of pronunciations are not actually categorical. Reading aloud is an example of a quasi-regular domain with a gradiated continuum stretching from regularity to exceptions. And there are also pronunciations that are a little bit less exceptional than others. In fact, a microstructural approach to quasi-regularity would entail moving just a little bit along the continuum. And neural networks are able to learn quasi-regular domains like reading aloud. One of the behavioral markers for how neural networks accomplish this is when knowledge of domain regularities is generalized to new examples. Meanwhile, exceptions are marked by minimal generalization, and a pronunciation that is less exceptional should be marked by some generalization. So, the big theoretical theme of this research is the question: how is quasi-regularity represented in a neural network? Our work builds on the theoretical contributions of Kim et al. And their account of representational warping. Generalization of a regularity in unwarped representation space could look like these words that share a regular pronunciation. The grid lines depicting this space are square and unwarped. Meanwhile, an exception, like pint, which is pronounced differently from its neighbors, exhibits a warping of the underlying representation space, which is depicted as a bulging of the grid lines. The neural network should not generalize knowledge about the exception to the neighboring representations that are pronounced regularly. So, warping the representation corresponds to less generalization. We examined representation warping and generalization in the following manner. Our study involved made-up words like this one, N-I-N-T. In this example, we assigned an exception pronunciation. Instead of being pronounced like its neighbors lint or mint, N-I-N-T was pronounced like pint, so this exception was pronounced nint. This exception, therefore, has a minimal level of generalization from what we know about the pronunciation in the rhyme neighborhood. But what if we wanted to make this a little bit less exceptional? The way we approached it in our work is to go to neighboring non-words, in this case F-I-N-T, and we train the model to pronounce it as fint, as if it were a real word. Watch the representation space as it distorts. As this pronunciation is also an exception, the representation space around fint has become warped, similar to the way nint was warped. The space between fint and nint is now a little bit less warped, corresponding to this newly shared pronunciation. And if we want to make our exception even a little bit less exceptional, we can continue this practice. For the next neighboring non-word, R-I-N-T, we will assign this an exceptional pronunciation as well. Once again, watch how the representation space is altered by the exception. Now, within this region of similar pronunciations, we have a new consistency, and slightly more generalization is going to be possible among these words. It is still notable that the regular pronunciations in the neighborhood, like lint and mint, remain on the unwarped portion of the representation space. In effect, we are controlling the consistency of pronunciation by manipulating the onsets of these made-up words in order to create new contexts for rhymes. In the example visualized here, we created 3 new contexts, nint, fint, and rint, for the rhyme stem int, thereby increasing context variability. And previous research has already established a relation between context variability and language learning. In our study of language learning, we used a neural network model that approximates the performance of an adult English language speaker. This model, which is an extension of Plout et al., is trained with a baseline vocabulary of about 3,000 monosyllabic English words. Once the model gained proficiency with the base vocabulary, we continued training 3 different versions of this model. The only difference between these models was whether they learned 30, 60, or 90 new made-up words. These made-up words were evenly split into regular, ambiguous, and exception pronunciations. For example, the network that learned 30 new items was trained on 10 regulars, 10 ambiguous, and 10 exceptions. I will explain in a moment how this enabled us to manipulate context variability. We call these new training words anchors because they establish reference points in our pronunciation representation space, and we can refer back to these anchors during testing. In order to test generalization, we use special non-words that the network was never trained with that we call probes. We essentially probe the representation space, and we ask the network how it would pronounce the probe word it's never seen before. So, in the case of nint, rint, and fint, we could ask this network how it would pronounce a new non-word, S-I-N-T. Depending on the representational neighborhood of the probe word, the network could potentially pronounce it in several ways. Based on this neighborhood, it could either be sint or sint. By now, we've seen how an exception pronunciation can have 1, 2, or 3 new contexts, like in the case of nint, fint, and rint. And we've seen how the network can be tested by asking it to produce a pronunciation for an untrained non-word probe like S-I-N-T. Although just one probe is shown here, we actually generated 4 probes for each anchor. In this case, the correct pronunciation should sound like pint, not mint. This process can be repeated for regular anchors too. Here are new contexts, NISP, FISP, and RISP, which can be probed using the non-word KISP with the expectation that it will be pronounced to rhyme with lisp. And somewhere in between regulars and exceptions are ambiguous anchors like BIVE, which could be pronounced biv or bive, but in this case it's bive. 1, 2, and 3 new contexts were created, bive, kive, and tive. The pronunciation can be probed with MIVE, and the model should generate a pronunciation that rhymes with dive, not give. We call this a dilution manipulation because we don't just want to increase the number of training examples as we introduce additional contexts. Instead, we hold the number of training examples constant, even as we vary the number of contexts. In the high dilution condition, where there are 3 contexts, we train each with a frequency of 1/3. In the moderate dilution condition, where there are 2 contexts, we train each with a frequency of 1/2. And in the low dilution condition, there is just 1 context and we don't reduce this frequency at all. In summary, as dilution increases, we present each context fewer times while keeping the overall frequency for the rhyme stem constant across dilution conditions. Now, let's look at the performance of the model before and after training with our anchors. Regulars are pronounced correctly even before training. This result demonstrates generalization of previous knowledge to novel examples. For the ambiguous anchors, we can see that prior to training, the model guesses the pronunciation correctly almost half the time, which is a pretty good confirmation that these anchors are, in fact, ambiguous in their pronunciation. Ambiguous knowledge is only going to generalize some of the time. And when we look to the exceptions, these are always mispronounced prior to training, which confirms that we did in fact construct exception anchors that do not share pronunciations that exist in the English language. In other words, previous knowledge does not generalize to produce the exceptional pronunciation. After training, all anchors, whether regular, ambiguous, or exception, were learned to be pronounced perfectly, and in fact this was true for all dilution conditions. Next, we look to the performance of the probes, which is a way of assessing the generalization from the knowledge gained by learning the anchors. We first examine the ambiguous probes, and we find a replication of Armstrong et al. In which training with these new anchors increases generalization already. However, we expected to find a more complex pattern of results. As these ambiguous terms become a little bit more regular, we expect to see incrementally more generalization. Therefore, across dilution conditions, we expect to see more generalization in terms of training consistent pronunciations. And that is what we see, an incremental change in pronunciation accuracy as dilution increases, corresponding to an increase in generalization. In this manner, we are exhibiting fine control over the microstructure of this generalization mechanism. We expected to see something pretty similar with the exception probes and the exception anchors. Now, this will be at the other end of our quasi-regularity dimension, and as the exceptions become a little bit less exceptional, we expect them to exhibit a little bit more generalization as dilution increases. And that's what we find. Generalization increases as dilution increases, as the exceptions become slightly less exceptional. Also, by the way, regular probes always produced training consistent responses, irrespective of dilution level. Now, we've seen something similar in other word learning studies. For example, Gherkin 2006 looked at infant word learning in which the final syllable of their stimuli was manipulated to either be constant across all examples, basically a no variability condition, or to be variable across examples. And they found increased generalization in the high variability condition compared to the no variability condition, which can be interpreted as supporting a relationship between context variability and generalization in a quasi-regular domain. We would also expect to see these generalization phenomena in domains beyond language. For example, in the case of birds, a blue jay and a robin will be fairly typical examples for the Toronto region. These are both birds and they both fly. A slightly stranger Canadian example is the loon, which has wings and flies, but it also swims. And then a penguin has wings, doesn't fly, but it does swim. These examples illustrate how concepts and categories are organized in another domain with a representation that is modulated in a graded and continuous fashion. In conclusion, this work has been an exploration of knowledge representation warping at a microstructural level, probing the effects of incremental changes to the consistency of our quasi-regular domain. We've demonstrated evidence that representation warping can be modulated, which helps to explain the continuous nature of quasi-regularity. Altogether, this is a step towards understanding the way representation, learning, and generalization are interdependent components of human cognition that interoperate to do more than what any one of these individual components does when examined in isolation. Thank you very much for your attention. I look forward to answering any questions you might have.